So welcome. So here we are on doing these fluid dynamics. This is fluids in motion. And this was something that as a student in my day wasn't talked about that much. And in fact, we're not going to talk about that much on this. But you could divide this world up into the laminar flow regime and the turbulent flow regime. And laminar flow is that smooth blowing air or water that's coming out of your tap as a nice like little tube of water. And then, it gets windier, so it starts getting blustery. Or you turn the tap higher and it starts to sputter. And that's turbulent flow. The same tap, the same water, just going faster, different behavior. Same wind, same air, just going faster. It's the way it goes. There's a point at which basically turbulence is introduced into the system. And mathematically it gets chaotic. And in fact, that's what happened in a kind of coincidental way. There was a group of students, and I think they dropped out of college. I think they were the kind of like that classic bright, but undisciplined kind of crew who basically found their undergraduate, I think it was physics, but it might have been something else, a bit boring, and weren't getting much out of it. And they wanted to stay in science, and they were kind of like, they were living that life of, before you get responsibilities where you can basically, maybe with the well-to-do, I don't know. But they were basically living kind of like as students, but they weren't particularly attending classes. And one of them came across a paper, which is a kind of fascinating thing, which said that on some populations in isolated places like Antarctica or a desert island or something like that, all physics trains you to assume is that if you have foxes and chickens, eventually you will reach a steady state where you have just enough chickens to feed the foxes and just enough foxes to eat the chickens. That's what physics does. If you think about it, we always go for that equal sign. Number of foxes equals number of chickens, or not equals, but number of foxes, hunger equals number of chickens to be eaten, kind of thing, And where we have time variation, we have nice, functions that we can integrate or differentiate, So all of our training is that things go towards an equilibrium position and then everything's stable. But what they found is that in populations that are isolated, under some circumstances, then you get instability in the population. That is, one year the foxes eat too many chickens and the chicken population plummets. Will they survive? And then they look later and they have too many chickens and not enough foxes. The foxes kind of starved and did badly, and the chickens came back up because there weren't enough foxes to catch the chickens. And hundreds of years, if you imagine putting these foxes and these chickens on an island, hundreds of years later, there's still not this stability. They've not reached steady state, and it looks like they're not going to reach steady state. Now, in most physical states, it does reach steady state. So what's the issue? And the issue actually is the rate at which, the foxes, it's when you get high fertility, big possibilities within a year of expanding the population. It becomes very unstable. I think it was actually found with some animals in Antarctica. Huge population, huge litters of kits. And some years they'd plummet and some years they'd bounce back, but they'd never, reach stability. And people started getting curious about this, and they started realizing that in a way, that's what goes on in the weather systems. And in a way, that's what goes on in chaotic, those things that vibrate kind of like in wacky ways. And so they opened the door on a whole set of mathematics called chaos theory, which is been mined even to this day. It's in lots of places that you don't necessarily expect it. It has lots of manifestations. The idea, if you get the essence of chaos theory, is that a little change at the very beginning that might be imperceivable to you makes a huge change later on. So with those populations, there's a little change Something happens in that environment that's not obvious, and it changes how successful the foxes are at eating the chickens, etc. It's not necessarily, that change might be random, but the behavior is not random. Something is influencing it. And the symbol that they use is, in Africa, there's a butterfly sitting on a bush, and the Africa is trying to decide whether to stretch its wings or not. And it doesn't know, but if it does flap its wings, it causes a little pressure, which causes another little pressure, which gets added to and multiplied, and that becomes a hurricane. And if it doesn't flap its wings, then there's not that pressure to begin the whole thing, so there's no hurricane. So it's like, whoa, that's like, everything's set up for the hurricane, but I didn't flap my wings, so it doesn't. The time is gone. Flap my wings a couple of minutes later, nothing happens. Flap my wings this instant, everything's set up, I get the hurricane. So seemingly inconsequential differences at the beginning make huge differences at the end. And there's a whole bunch of physical systems where that works. So that's what's going on in this turbulent region. Now, when I was a student, I actually did engineering part 1 on fluid flow, and they talk about basically this is if the Reynolds number is such, we get this nice laminar flow, and if the Reynolds number is that, we get this turbulent flow, and we don't talk about that because we don't have the math to talk about that. And now the math is coming with this chaos theory. The math is coming. So it's becoming more and more part of our canon, but it's not in the textbooks yet, and it might never be in the textbooks. But it's this region, and if you never talk about it, people tend not to ask questions about it. So in a way, it was just never talked about before. It was just like, we won't discuss that. And the reason was they didn't have the skills to discuss it. So we have laminar flow. Each particle of the fluid flows in a smooth path. The paths of different particles never cross each other. Okay? If you're to the right of me, you stay to the right of me. You might get further away, you might get closer, but you stay to the right of me. If you're to the left of me, you stay to the left of me. The velocity of the fluid flow at any point remains constant in time. Now, there might be bits where we're going fast, and there might be bits where we're going slow, but where we're going fast, every particle is going to go fast. And where we're going slow, every particle is going to go slow. It's like traffic on the interstate. We all slow down at this one particular point, but we all slow down at that point. We don't do a constant speed throughout our journey, but everybody does a slow bit in this one particular point, and everybody goes fast at that point. And then the velocity flows, the fluid flows at low velocity. This is what tends to be the pattern. When you're flowing at lower velocity, you tend to get laminar flow. Take that same physical situation and just turn up the velocity, and then we start in this region here, in this region there, we start getting turbulent flow, and so the particles do not follow exactly the same path. You're in front of me, and maybe we'll diverge, and I'll go off one way, and you'll go off the other. Whirlpool regions exist. I might get caught in a little eddy current and just be lost for a while, and then spin back out of it. Paths of different particles do cross. Maybe you're to the right, now you're to the left, now you're to the right, now you're to the left, just going backwards and forwards. Velocity of fluid flow at any point changes in time. If you stand in a given position, you'll hear sputtering wind. It will be blustery. It won't be a constant howling. It will be blustery. And fluid flows at higher velocity. That's what causes it. The same physical situation, higher velocity. Kind of be able to distinguish between those. If I gave you 3 out of the 4 and one of them was wrong, if I gave you the 3 of them and one of them was wrong, could you say that one's wrong? That's like, identify the kinds of flow when particles cross paths. What would that be? You're crossing paths. Turbulent or laminar? It's turbulent. And identify the kind of flow when velocity of flow at a specific point never changes. Constant speed. All the particles, constant speed. What is that? Laminar, yeah. And identify the kind of flow when particles consistently flow at follow the same leader. Laminar, yes. This actually comes into, I'll give you a very practical situation. I had a vacuum evaporation system. So it consists of a vacuum pump, and then there'd be basically a hot filament, and I'd put gold wire on that hot filament, and then I'd have a glass plate, but I'd want the glass plate to be a certain pattern of gold on it, so I had what's called a photomask. It's basically just an etching in the metal holder, and I'd put the glass in there, and I'd evaporate, and I'd get this beautiful pattern of gold right where I wanted it. And what happens is the inside of this also gets covered in gold, so you begin and you can see everything, but at the end of the thing you can't see anything. You just do what you need to do, and then you let air back in and you take the system out. My predecessor was really a phenomenal scientist. He had it all, actually. He was really good. And he was the one who had all this constructed. And he was a bit, man, if I had any criticism, it was that he was a bit picky, you know. It's like everything was just... And he had these little metal clips in here. And they were a pain because you had to just get them just ready to push in on one and then put down on the other. You're dealing with this stuff, you don't really want to touch it that much. And now I had to get this thing and pull this clip out of the way and put it in. There was a couple of times when I scratched the thing, taking it out, and I didn't like those clips. So one day I just said, to heck with it, I'm taking these clips out. So I got the thing and pulled them out, you know. It's like I made the equipment my own. He'd graduated, he was gone, it was mine now. I'm not having those clips in there. I took ownership, you know. A weird thing happened. I didn't notice it immediately, but I noticed one time that when I took the system out, the gold was on the top face. Impossible. This is totally impossible. It should be on the bottom face because that's what this mask is about. The gold should actually be deposited there, and it was deposited on top. So, you know, in labs, there's jokesters around. I hadn't actually watched the whole thing. I'd done it, you know, had lunch or whatever, you know. Just by chance, I hadn't actually done this thing. So I figured my buddy had simply come in while I was out, flipped over my slide, pumped my system down again. Bit of a nasty thing to do, because if he scratched my slide, it'd have destroyed a sample for me. So it was a little bit, I thought it was funny, but it was a little bit, you know, kind of like over that line. And I kind of chided him for it, and he denied everything. Well, I was a bit upset, so maybe, you know, it was just like, you know, hey, I don't want to mess with him. So I denied it, you know. It happened again, but this time I had not left the room. And it's impossible. It's impossible. And then, just as it happened, just I think the next time or the time after, I was pumping down, and it was at vacuum, but I didn't have a good contact to all something about my gold source wasn't right. And so, oh man, I got to let this thing back up to air. And the way you let it back up to there is there's a valve in here, and you just open that valve. You just, and it takes maybe an hour to pump down. It takes maybe 10 seconds to come back up to air. And I'd been familiar with it, but you know, you could hear the gas going in, and I noticed that the source, which I think had cracked, was like vibrating a little bit as the air came in. And my slide, I swear my slide flipped up. And so what was happening was depositing gold on the underside, and then when I let the air back in, because it was turbulent, it was high-speed air coming back in, and it just, the way it was designed, it was like a bit wider on the top than it was at the bottom. So this thing flipped, and it could be a little bit out, but it would go settle back down in. And I've seen a couple of examples of that. There's one where they were using, in Scotland, they were using wine bottles as kind of floats under the water to kind of hold they'd basically drop a fishing line down, and then they'd pull it back up and they'd have a wine bottle that would mark, this is where we are kind of thing. And what was happening was this guy started marking the front end of his cork, and when he came back, he thought he saw that it had flipped, and so he started marking it, and when it came back, it hadn't flipped. And what they did was they put a video where they increased the pressure on the water, and what happened was when it got to deep enough in the lock, then the cork would actually push into the wine bottle, and water would flow into the wine bottle, and the cork would kind of like be there. And then when it drained out, it just happened that it drained out the other way. Just the dynamics of the thing was, it flipped the thing. So these things sometimes happen. So dynamic flow, the turbulent flow is kind of like usually to be avoided, but sometimes can have some interesting effects. We're going to talk about laminar flow, and we're going to talk about tubes. This first one is basically saying that traffic can neither be created or destroyed. So if I have so many cars a second on a one-lane highway, if I take the number of cars times the number of lanes, the number of cars per second times the number of lanes, at the beginning, I'll get that same number of cars times the number of lanes. So 3 cars a second going through one lane is like 1 car a second going through 3 lanes. Yeah. And the idea is that the volume of fluid or gas or whatever, well, fluid, non-compressible fluid, the volume of fluid that I let in any second must equal the volume of fluid that escapes in any second. If not, I have holes in here or I have extra fluid coming in. And you can't have either one of those. It's filled with fluid. So the volume per second flowing in has to equal the volume per second flowing out. Does that make sense? So the way we express that is we simply say, well, the volume, that's not volume, that's velocity. It's meters per second times meters squared, which equals volume per second. So it's the area of the inlet times the velocity of the water at the inlet is equal to the area of the outlet plus the velocity times the velocity of water at the outlet. You know this. If you're watering the garden with a hose and you can't get to that bush over in the corner, what do you do to get to that bush? You put your thumb over the end. You're reducing the A to increase the V, which means it goes further. You kind of know it intuitively, So this is called the continuity equation because it's the continuity of fluids. And it's just A1V1 equals A2V2. Most people get confused because they think that the V is either volume or something like that. So just make sure you know as always, make sure you know what the terms mean. A pipe has an entrance area. So this is 8 square meters. An exit area. It doesn't have to be small, it could be going the other way, but in this case it's smaller. 2 square meters. And you enter at 5 meters per second, and you exit at V meters per second. And what we say is A1 V1 is equal to A2 V2. And so this would be 8 times 5 is equal to, it's going to be 2 times V2. So V2 is equal to 8 times 5 over 2, which equals 40 over 2, which equals 20 meters per second. There it is. It's not bad. It's like put your teacher's hat on. So what would you do to make this a little bit more interesting? You need the radius. Then you've got to work out the area. And you'd be amazed at how many people will put down A1, V1, but they'll use just the radius for the A. That's not visualizing. That's not that they can't do math. It's that they're not visualizing to know what math to do. And so you got to visualize. We try really hard to avoid this becoming a plug and chug course where if you know the equation, just shove numbers and you get the answer. So, and it's just the way it is, because engineers don't just shove numbers into equations, they visualize. So it's important that you build these visualization skills. That's one thing I could do. I could mess with the unit, centimeters per second and all that kind of stuff, but that's the big thing I can do. Is I could use prefixes, micrometers squared and all that kind of stuff, and still catch. Some people still don't know the prefixes. If you end up at upper division courses and you don't know your prefixes, you will not be taken seriously. There's some things you cannot know. It's like, fine, they missed it. But something fundamental like that, if you go in and you don't know your centimeters squared from your micrometers squared from your meters squared, they'll just like, and you'll be the conversation will not include you anymore. So if you're not there yet, you just got to get there. It's just like, it's got to get there. Last thing, Bernoulli's equation. So this is basically you get big pressure differences. So you got volume of water coming in, you got velocity of water coming in, you get velocity of water coming out. You get an area coming in, you get an area coming out. But they say the difference in height is so great that you get differences in pressure. So it's more complicated, and I can't justify this equation to you at all. I can tell you that, the units are consistent. So pressure is in newtons per square meter, and Newton is force, so this would be, my pen, this would be kilogram, that's kilogram meters per second squared. That's mass times acceleration, that's force, divided by meters squared, that's area. So that's kilograms over meters second squared, yeah? That's that first one. And then density is kilograms per meter cubed, and I'm going to multiply it by velocity squared, which is meters squared over second squared. And when I play this one out, it goes kilograms over meters second squared. So those two match. And then we'll look at my third one, which is density, which is kilograms per meters cubed, times G. G is, man, this is a long one. This is kilograms meters per second squared, that's newtons over kilograms. And then H is in meters. So I end up with, let's have a look, those kilograms go with those kilograms. I end up with kilograms, that H is on top. So I get over meters seconds squared. So I get the same thing again. So I can tell you that's the same units as that is the same units as that, but I can't justify. So that means that it's allowed to be in an equation together. If they're not, you can't put plus signs there and all that. You add apples to apples. You don't add apples to, rockets. It doesn't go. So I can justify it in terms as much as that, but I can't tell you, I don't know the derivation of this equation. Let's do one. Pipe's entrance height is 2 meters above. And the water pressure at the entrance, 90 Pascal. It's very low pressure water. Speed at the entrance is 8 meters per second. The density of water, so density is equal to 6 kilograms per meter cubed. And the exit pipe is 4 meters above. And exit pressure is 50 Pascal. And show that the speed of water is. So what is V exit? That's what it wants. It wants show that it's that means what is it? It's just so that we have an answer to look for. So P1 plus 1/2 rho V squared. Isn't that like a half mv squared? It's a bit like kinetic energy, isn't it? Plus, what was it? Rho GH is equal to P2 plus 1/2 rho V2 squared plus rho G8. I've got to tidy my subscripts up. That's 1, that's 1, that's 1. This is 2, that's 2, that's 2. Agreed? So I look at my diagram and I go 90 plus 1/2 times 6 times 8 squared plus density is 6 times 10 times 2 is equal to, now that's 50 plus 1/2 times 6 times V squared plus 6 times 10 times 4. 90 plus 3 times 64 is 124, 132, I think. 64, no, that's not right. 3 times 6 are 18, 192. That's to get a calculator to check that kind of thing. I'm being a bit off here. And that's going to be 120 is equal to 50 plus 3V squared plus 240. So that's going to be 90 plus 192 plus 120 minus 50 minus 240 is equal to 3V squared. So I do want my calculator for this. So that's going to be 90 plus 192 plus 120, enter, minus 50, enter, minus 240, enter. That's 112 divided by 3 equals 37.3. Second square root, second answer is 6.1. Yeah, good. So V is equal to 6.1 meters per second. So it's just long. Don't have a... Where I remember this is, it's about pressure. It's got something that's similar to a kinetic energy in it, and it's got something that looks a bit like potential energy in it. But it's rhos rather than m's, you know. Cool. So there we have it.